Hi, welcome to the portal. Today's lesson we are going to talk about electrostatics. Okay, so this lesson it will be mostly grade 10 and grade 11's work. Okay, guys, because in grade 12 we are doing the electrostatics that we did in grade 11. Okay, so there's no new content in grade 12 for electrostatics. Okay, so guys, before we continue the video, please, if you have not subscribed, please subscribe and like the video. Okay, so now here are the notes that I've compiled together so that you can revise with. Okay, so now you can go through this, you can pause the video and go through this on your own. Okay, so now this topic is under the quantization of charge. Okay, so now the basic unit of charge called the elementary charge, E, is the amount of charge carried by one electron. Okay, so now do not be confused when I say called elementary charge E. This E can be used interchangeably with QE. Okay, so sometimes they can write E, sometimes they can write QE. Okay, so now what is this E or this QE? It is the charge carried by one electron. Okay, so now this second point also illustrates that. Okay, so the charge on one electron, okay, QE 1.6 times 10 to the power minus 19 coulombs. At the back of your question paper you will find this on your data sheet. Okay, so you must be able to use that. So now the principle of quantization of charge. Okay, there is the definition there. All other charges in the universe are integer multiples of the elementary charge. Okay, read it again. All other charges in the universe are integer multiples of the elementary charge. We know now what is an elementary charge. Is QE, which is 1.6 times 10 to the power negative 19 coulombs. Okay, so all charges in the universe, they are integer multiples of that, meaning we can multiply that QE by negative value or by positive value, but that value must be an integer. Okay, so you will notice that integers, they also include 0. Okay, so they have 0, so it's possible that there might not be a charge, an object might not be charged. So if an object is not charged, it means 0 multiplied by the elementary charge. Okay, so now this principle of quantization of charge, the formula of principle of quantization of charge is this. So charge, it is equals to number of electrons multiplied by the elementary charge. Okay, so charge on an electron, it will be, if we have one electron, it will be charge is equals to 1 multiplied by what? 1.6 times 10 to the power 19 coulombs. Okay, so if I had 2 electrons, it was going to be 2 times that number. If I had 5, it was going to be 5 times that number. If I have 1,000,000, it was going to be 1,000,000 multiplied by that number, and then the charge would be something that is greater than the elementary charge. Okay, so this is what it means that charge is quantized, meaning it exists as a multiple of the integer. Okay, so now the basic unit of the charge is what is coulombs. So coulombs is capital letter C. Okay, capital letter C, and then the symbol of charge is capital letter Q. Okay, so and then this N, do not be alarmed when I've written it as a capital letter here. It's the same thing as this small letter 1. Okay, so now here's a statement that I want you to check. Okay, so an object with a charge of 0 has neither excess electrons nor excess protons, or what you can say electron deficient. So what do I mean by this? I mean that if an object has a charge of 0, like this one, you can see that we have aluminium here. So this aluminium is neutral, so meaning here the charge is 0. I don't have -1, I don't have +1, so meaning it is not electron deficient, and it does not have excess electrons as well, so it has a charge of 0. This is what this statement means. Okay, so again, another point, it's an object with a negative charge has excess electrons. Okay, so now Cl minus has 1 minus there, you see, so it has excess electrons. And then an object with a positive charge has excess protons. Okay, so you will hear these terms in some questions asking you that calculate the number of excess electrons, calculate the number of excess protons, or what is the charge if the excess protons are this number. Okay, so don't be scared. So positive charge has excess protons, or what we can say is that it is electron deficient. Okay, so and when I say excess protons, I don't mean that they have added protons to that atom. You cannot add protons to an atom. Okay, it's just that when an atom loses electrons, it will have more protons than electrons, so we can say that those protons are in excess. Okay, yes, that's what it means. So now here we have example 1. An object has a charge of that. How many excess electrons does it have? How many excess electrons does it have? So what is this? This is something like this, right? There is an object, object X. Okay, so this object X, it is negatively charged, so it is X minus. Okay, so because it is negatively charged, it has excess electrons. So they're asking how many excess electrons does it have, because we can see it as a negative charge. Okay, so it means if it was an atom, it will be an atom that has a excess electron like that has a negative at the top. Okay, so they're asking how many electrons does it have. So what can we use? So we know the charge, we are given the charge. Okay, so what can we use? We can use principle of quantization of charge. Okay, here I've rewritten principle of quantization of charge. I rearranged it, so this is the same as this, N, and here QE. Okay, so what happens here is that I divided both sides by QE to make N subject of the formula. Okay, so now what am I going to do? I'm going to take my Q, which is my charge, is minus 1.92 times 10 to the power minus 19 coulombs. Okay, so I'm going to divide it by what? By elementary charge. Remember, we are talking about electrons. Okay, we are talking about electrons. So this elementary charge, although it is given as a positive at the back, when we are talking about excess electrons and stuff, so if you see that your charge is negative, your elementary charge, remember, it is an integer multiple. So because it is an integer multiple, it can either take positive or negative. Okay, so here we are going to choose negative. 1.6 times 10 to the power minus 19 coulombs. Okay, so now what's going to happen? We can see that coulomb is going to cancel coulomb here. Okay, so and then negative is going to cancel negative. Okay, so 1.92 10 to the power minus 19 over Okay, so oh, that's 17 at the top. It's not 19. Made a mistake here. It's 17. 17. Okay. 17. So it gives me a total number of 120 electrons. Okay, 120 electrons. So this is a number. Electrons are real things, guys. So the number of electrons, it cannot be negative, it will be positive. So what happens is this: when you calculate the number of electrons using quantization of charge, if your charge is negative, your elementary charge must have a negative number as well, so that negative divides negative. Okay, and if your charge is positive, your elementary charge must be positive as well, so that positive divides positive and you'll end up with a positive number. Okay, guys, so there you would get 3 marks there. You get a mark here: 1, 2, 3. Okay, so yeah. Okay, now we have example two identical metal spheres A and B of charges -3 nanocoulomb and -5 nanocoulombs respectively are placed separately on insulating stands. Okay, so now this looks like this. Okay, this distance R there. So this is A, this is B. So A is -3 nanocoulomb and then B is -5 nanocoulombs. Okay, so they did not tell us about the distance. Okay, so if the charges are brought into contact with each other and then separated again, okay, so calculate the charge on each sphere after contact. Okay, so what happens is that they are taking these two charges, they put them together into contact. Okay, so now because these two spheres, they are conductors, remember they are metals are conductors, so they are going to act as one charge, and then the charge will spread throughout two spheres, acting as if it was one object. Okay, so as soon as we separate the two spheres, so that charge will be divided into two, because we have two spheres that are identical, meaning they are equal in size, they have the same material, so they are going to distribute the charge evenly. So they are going to share the charge, they will divide the charge in half. Okay, so now what it means is that when I calculate, when I separate them, each sphere will have half the total charge of the spheres. Okay, so now here's the formula that you will use: calculate the charge on each sphere after contact. So you will say Q is equals to QA is -3 nanocoulombs, -3 times 10 to the power -9 coulomb plus into -5 times 10 minus 9 coulomb divided by 2. Okay, so now I have -3 -5 is -8 divided by 2. So here I have -8 times 10 to the power 9 coulombs divided by 2. And then what am I getting? I'm getting that each sphere will have a charge of -4 nanocoulomb. Okay, so that is the charge on each sphere after contact. So now 2.2, sphere A and sphere B. Between sphere A and sphere B, which sphere is going to transfer electrons to the other, and how many electrons? Okay, first of all, we have to check which one is more negative. Okay, so the one that is more negative, it is the one that is going to transfer electrons to the other, so that the other one will have a charge of -4. So if you can check this -5, it will transfer one electron to this -3, so to make this -3 -4. So this one, after losing that -1, it will be -4. So I will have -4 -4 after contact. Okay, so B is going to transfer the electrons to A. Okay, now B B will transfer excuse me, the app I am using is not really good in terms of writing. B will transfer electrons to A. Okay, and then they're asking how many electrons will be transferred from B to A. Okay, so what am I going to do is this: I have to check the initial charge and final charge of B. Okay, so I'm going to say the change in charge of B. Okay, so I have charge, the final charge minus the initial charge. Okay, so the final charge, I have -4 times 10 to the power -9 coulombs. Okay, minus into what was the initial charge? Initial charge was -5 times 10 to the power -9 coulombs. Okay, so now here I have -4 plus 5, so I have 1 times 10 to the power -9 coulombs. Okay, so we can see that this sphere B, it has lost electrons, because now the difference, we get a positive charge, we get a positive value, so it has lost this amount of charge. Okay, so how many electrons did it transfer? Okay, so the electrons will be electrons from this charge. Okay, so now we are going to say N is equals to Q divided by QE. Okay, so now 1 times 10 to the power -9 divided by 1.6 times 10 to the power -19. Okay, so how much do we have? We have 6.25 times 10 to the power 9 electrons. Okay, so that is the answer. So now let's jump to Coulomb's law. So now the Coulomb's law states that the magnitude of the electrostatic force between 2 points charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Okay, so it is defined by that formula as well, as you can see. Okay, so this force is directly proportional, the magnitude of this electrostatic force is directly proportional to the magnitude of the product of the charges and inversely proportional to the square of distance between these charges. Okay, so now this K is what we call electrostatic constant in free space, so it is given by that constant. Okay, so now here's the relationship of the direct proportionality. So the electrostatic force is directly proportional to the product of the two charges. What does this mean? It means that if one of the charges increases, let's say for example Q1, the magnitude of Q1 increases, what will happen to F? F will also increase. Okay, so and if one of the charges, let's say Q2, decreases, right, and then if Q2 decreases and distance remains the same, and Q1 remains the same, and then F will decrease as well. Okay, so whatever happens on Q1 and Q2, if Q1 and Q2, if the product increases, F will increase as well, provided that the distance remains the same. Okay, so here what happens is that we have inverse proportionality. So if the distance between two point charges increases, the electrostatic force will decrease as well. So if R increases, F will decrease. Okay, so we can have an example, a quick example. Okay, so if I have charges Q1 and Q2, okay, and distance R, okay, and then they give me a force of F. Okay, so if Q1 and Q2 they give me a force of F, right? So what happens if one of the charges, let me write it here, what happens to F if one of the charges doubles while the distance remains the same? While R remains the same. Okay, so what is going to happen here? So I'm going to have this. So it's going to be K, Q1, Q2. So because if it doubles, one of them doubles, it means I will have this, let's say Q2, Q1, and then here I have Q2 divided by R squared. Okay, so now what is this? We can see that here we have a number. I can put this number here. I have 2K Q1 Q2 divided by R squared. Okay, so now, but we know that K Q1 Q2 over R squared is equal to F. Okay, so I have 2 multiplied by F. You see, so now if one of the charges doubles, the force will also double. Why? Because force is directly proportional to the product of the charges. This is the reason. Okay, so you find this kind of problem in multiple choice questions. Okay, so you can also have another scenario whereby what happens if the distance halves, okay, while the charges remain the same. If if R is now 1 over 2, what was initially, okay, so if our distance is half R, what is going to happen now? Okay, so if our distance is 1 over 2R, so this is going to happen. So K Q1 Q2 over 1 over 2R. Okay, so all squared here. So now 1 over 2 all squared is 1 over 4. Okay, so now here I have K Q1 Q2 divided by 1 over 4 R squared. Okay, so now here notice that I have how many divisions I have. 1, 2. So if I change this division, it's going to be something like this. Here I'm going to have k q1 q2 divided by r squared multiplied by 4, because I'm changing division to multiplication. Okay, so now this 4, notice that it's going to multiply everything here, and what is everything? Everything is half, is f. Okay, so the final answer is 4f. So if my distance is halved while the charges remain the same, while the magnitude of the charges remain the same, the force will quadruple. If my distance halves, my force will quadruple. Okay, so now this relationship tells us about the inverse proportionality, because the distance is decreased but the force is increased. You see, so when distance when r is decreased, f is increased. You see, so know this kind of questions, know how to answer this kind of questions, because they ask these questions in multiple choice, guys. Okay, so now example 1, 2 point like charges carrying charges of 3 nanocoulomb and minus 5 nanocoulomb are 2 meters apart. Determine the magnitude of the force between them and state whether it is attractive or repulsive. Okay, so what happens here is that we have two spheres. Okay, we have 2 point charges that are separated by distance 2 meters. Okay, so now they want us to calculate the magnitude of the electrostatic force between them. Okay, so what do we do now? What are we going to use? We are going to use Coulomb's law. What does Coulomb's law say? F is equals to k q1 q2 divided by r squared. Okay, so what is k? K is 9 times 10 to the power 9 multiplied by q1. Q1 is positive 3 nanocoulombs. Okay, so nanocoulombs multiplied by, here we are not going to include this negative because we are talking about their magnitude only. That negative gives us direction, so we will not include it in the Coulomb's law formula. Okay, so divide by r squared. How much is r? R is 2 meters. Okay, so notice that here we work with SI units, so this r, it needs to be in meters. If it is not in meters, you have to convert. Okay, so now I don't have to convert because it's in meters. So now I proceed to press my calculator. Okay, 9 times 10 to the power 9 multiplied by 3 times 10 to the power minus 9 times 5 times 10 to the power minus 9 divided by 4. Okay, so now the force that I get is 3.38 times 10 to the power minus 8 newtons. Okay, newtons. So now this is the force that I got. So now the other question asks whether is this attractive or repulsive. Okay, so how am I going to know if it's attractive or repulsive? I have to check my signs. Okay, so I have positive, I have negative. Okay, so because I have positive and negative, these charges are unlike charges. Okay, so they attract each other. So because it's positive and negative, we say it is attractive. Okay, attractive. So let's go to example 2. So 3 points, 3-point charges are in a straight line. Okay, their charges are q1, q2, q3. The distance between q1 and q2 is that it's Okay, and the distance between Q2 and Q3 is that. Okay, what is the net electrostatic force on Q due to the other two charges? So we are calculating the net electrostatic force on Q2 due to other charges. Okay, so what are we going to do? We have to calculate the magnitude of the electrostatic force at this point due to Q1, and also the electrostatic force at this point due to Q3. Okay, so after that we have to do the resultant of that electrostatic force. Okay, remember that force is a vector quantity. Okay, so now here I have three point charges. Okay, so now what happens is this one is positive, okay, and also this one is positive. So this is positive, this is positive, okay, and this is negative. So remember, positive and positive, there like charges, they repel each other. So this one is going to repel this one to the right. Okay, so it's going to repel this one to the right. Okay, and what about this one? This one is negative, you see. So negative and positive, they attract each other. It's going to try to attract it towards the right as well. So it's going to attract it to the right as well, you see. So now all our forces, they go towards the right. Okay, so what is our resultant going to be? Our resultant is going to be these two vectors added together. Okay, so it will be something like this. Okay, our FR. Okay, so here I have the force of Q2 due to Q1, and then here Q2 due to Q3. Okay, so and then the resultant is FR. So let's go ahead and calculate the magnitudes. Okay, so now magnitude of let's start with a 2. Okay, 2 on 1 on 2. Okay, 1 on 2, force exerted by 1 on 2. Okay, so K Q1 Q2 divided by R squared. Okay, so 9 times 10 to the power 9 multiplied by Q1. How much is Q1? Q1 is 2 times 10 to the power minus 9 multiplied by Q2, 1 times 10 to the power minus 9. Okay, so divided by the distance between Q1 and Q2, the square of distance between Q1 and Q2. So I have 2 times 10 to the power minus 2 meters. Okay, all squared. So I don't have to write that because I haven't involved units anywhere. Okay, so I proceed to press my calculator. Okay, so I am getting 45 times 10 to the power minus 6 newtons. Okay, so and then now I'm going to calculate another one, F3 on 2. Okay, so it will be given by FKQ Q2 Q3 divided by R squared. Okay, 9 times 10 to the power 9 times 1 times 10 to the power minus 9, 19. Oh, minus 9, yes, because it's nanocoulombs. times that is q3 negative 3. Okay, that is 3. Okay, 3 times 10 to the power minus 9. Okay, so don't forget we don't involve negatives on this equation, okay, because we are calculating the magnitude of the electrostatic force. Okay, so the r, the distance between the two, okay, it's 4 times 10 to the power minus 2, okay, all squared. That's 9. Okay, so I am getting 16.88 times 10 to the power minus 6, okay, newtons. So here we can see that the longer one, the one with the larger magnitude, is 1 on 2. Okay, so this one is 1 on 2, this one is 1 on 2, and this one is 3 on 2. Okay, so we have calculated the magnitude of this one due to of q2 due to q1, and the magnitude of q2 due to q3. Okay, so now we have to calculate the net electrostatic force. So now from this vector diagram we can see that the net vector goes to the right. Okay, so meaning that our F net, we know that net is the sum of the forces. Okay, so initially 1 on 2 plus 3 on 2. Okay, so fortunately all of them, they go to the same direction, so it's all positives. Okay, so I'm going to have 45 times 10 to the power minus 6 plus 16 times 10, 16.88. Okay, 16.88 times 10 to the power minus 6. So 45 plus 16.88. So I have 61.88 times 10 to the power minus 6 newtons. Okay, so now that is the net electrostatic force on Q2. We have answered the question, guys. Okay, so if they ask you to give direction, it's 61.88 times 10 to the power minus 6 to the right. Okay, to the right. Okay, so let's do another example. Let's do another example on Coulomb's law. So 3-point charges form a right angled triangle. Their charges are Q1, Q2, and Q3. Okay, so the distance between Q1 and Q2 is that, Then the okay, and the distance between Q1 and Q3 is that. Okay, what is the net electrostatic force on Q1 due to the other two charges if they are arranged as shown? Okay, so here we can notice that we have a right angled triangle. So we have something like this. Okay, we have a 90 degrees there. Okay, and then here we have distance 5 times 10 to the power minus 2. Here we have 3 times 10 to the power minus 2. Okay, so what does the question say? What is the net electrostatic force on Q1 due to the other two charges if they are shown below? Okay, so now if you can check here, this is the scenario. If this is Q1, right, Q3 is negative, Q1 is positive, so there's force, there's attraction between this. Okay, so now Q1 is being attracted towards Q3, okay, upward. Okay, but what about the force this on the horizontal plane? Okay, so Q1 is being repelled towards the left by Q2 because Q1 and Q2 are positive, so it's being repelled towards the left. Okay, so this one is F13 and this one is F12. Okay, so you will notice this that since this is a right angled triangle, this will give us the magnitude here. Okay, so we'll have the magnitude there. So if I can shift this vector and put it here, I will have that a right angled triangle, and this one will be my FR. Okay, so I can find this FR using Pythagoras theorem. Okay, so now I know that F12 is my what? My adjacent, and my F13 it will be my opposite. Okay, it will be my Y, this one will be my X, and this one will be my R. Okay, so that's how we are going to solve the problem. So we are going to calculate the magnitude F12 and magnitude F13, and then we do a Pythagoras theorem to get FR. Okay, now let's continue. So F12, okay, Q1 Q2 divided by R squared, okay, 9 times 10 to the power 9 multiplied by Q1. How much is Q1? It's 4 nanocoulombs. And then how much is Q2? 6 nanocoulombs. Okay, so the distance between Q1 and Q2, it's 5 times 10 to the power minus 2, okay, all squared. So now what does our calculator say? Times 4. So 86.4 times 10 to the power minus 6 newtons. Okay, let's calculate F13. So F13 Q1 Q3 divided by R squared. So 9 times 10 to the power 9 multiplied by 4 times 10 to the power minus 9, okay, multiplied by Q3 is 3 nanocoulombs divided by R squared. How much is R? Is 3 times 10 to the power minus 2 all squared. Okay, okay, so here I have 120 times 10 to the power minus 6 newtons. Okay, so now Fr, which is my resultant, so because of that triangle, I'm going to have f squared by Pythagoras, f squared, fr squared plus f12 squared plus f13 squared. Okay, we know that this one is what is fr is equals to the square root of f12 squared plus f13 squared. Okay, so now f12, how much is f12? So f12 is 86.4. 86.4 times 10 to the power minus 6 times 10 to the power minus 6 all squared plus 120 times 10 to the power minus 6 all squared. Okay, so the square root of all that, how much are we getting? Plus 120 so I am getting 1.48 times, oh okay, let me put it like this, let me put it in the same scientific notation as these ones. 147.87 times 10 to the power minus 6 newtons. Okay, so you'll notice that it is greater than f1 and f13 because it is the resultant. Okay, so this is the resultant when you are given the arrangement in a right angled triangle like that. That's what you do, guys. Okay, so now there is a problem. You can attempt this problem on your own. It's similar to the first one that we did. Also problem number 2, you can try it on your own. Okay, so pause the video and I will write the solutions. You will check what are the solutions. Okay, pause the video. Okay, so now let's do problem 1. So it says for the charge configuration, show calculate the charge on Q3 if the resultant force on Q2 is 6.3 times 10 to the power minus 1 newtons to the right. Okay, so and then they gave us the charges there and the distances. So let's repeat the question. For the charge configuration shown, calculate the charge on Q3. Okay, if the resultant force on Q2 is 6.3 times 10 to the power minus 1. Okay, so what happens is that the resultant of this the resultant of the electrostatic force felt at Q2, right, is to the right, and it is due to what, to Q1 and Q3. Okay, so meaning that the resultant is given by what, F 12 and what f 23. This should be the resultant. Okay, so but we know that q2 is what is negative, so it's going to attract q1 towards the right. So we don't know about q3. Okay, we don't know about q3, so we don't know if it's positive or negative, but then we are told that the resultant is towards the right. Okay, so it's positive. So what am I going to do? I'm going to choose right as positive. Okay, so choose right as positive. Okay, choose right as positive. So now the resultant force is 6.3 times 10 to the power minus 1 is equals to F12. F12, I can get F12. Okay, so F12 can be given by 9 times 10 to the power 9 times Q1 is 4.36 microcoulomb multiplied by 7 10 to the power minus 7 coulombs divided by so the distance between Q1 and Q2 is given by R1 plus R2. Okay, so it's R1 plus R2, so it's going to be 1.85 times 10 to the power minus 1 plus 4.7 times 10 to the power minus 2 all squared. Okay, plus F23. Okay, so F23 we know that it's 9 times 10 to the power 9 multiplied by charge 2 multiplied by Q3. Okay, how much is charge 2? Charge 2 is 7 7 times 10 to the power minus 7. Okay, multiplied by Q3, so divided by what? Divided by 4.7 times 10 to the power minus 2 all squared. Okay, so now I'm going to press my calculator. Okay, so in here I have 6.3 times 10 to the power minus 1. Okay, and then now I'm going to press this whole sum, this large sum, 1. Okay, here I have 510.329. Okay, let's say 0.3 times 10 to the power minus 3. Okay, and then now the 9 10 to the power 9 times 7 to the power minus 7 divided by 4.7, so minus 2 all squared. Okay, so plus 2.85 2 times 10 to the power 9 Q3. Okay, so now what I'm going to do, I'm going to transpose this, take it to the other side. Okay, so now I'll have 6.3 times 10 to the power minus 1 minus 510.33 times 10 to the power minus 3 divided by 2.852 times 10 to the power 9 is equals to Q3. So Q3 is equals to 6.3 10 to the power minus 1 minus 510.33 times 10 to the power minus 3 divided by 2.852 times 10 to the power 9. Okay, so how much am I getting? I'm getting 4 point 4.20 times 10 to the power minus 11 coulomb. Okay, this is the charge that I'm getting, so it tells me that it's positive. Okay, so now this positive charge is being attracted towards the right. Okay, so yeah, also the problem number two it's similar to that example that we did. So calculate the resultant on Q2 given this charge configuration. Okay, so the point of interest is Q2. Okay, so if this is Q2, Q2 is negative, right? And Q3 is negative as well. So meaning Q3 repels Q2, so it repels it upwards. Okay, and then now Q1 as well is also negative. It repels it to the right. Okay, it repels it to the right. It repels it to the right. So now what happens? This one is F23. This one is F12. Okay, so now the resultant between this is going to come from here. Okay, so now if I can shift this vector, I put it here, and then I have a right angled triangle. So this one is my FR. Okay, so if you can calculate the magnitude of F12 and also the magnitude of F23. Okay, and then you do this, you say FR is equals to the square root of F12 squared plus F23 squared, and then you get FR. Okay, so and then that is your answer. And oh, if you're asked for you to calculate direction as well, if you are also asked for a direction, what do you do? There's a problem that we should have calculated direction. Okay, what is the electrostatic? What is the electrostatic force on Q1 due to other charges if they are arranged as shown? Okay, so here we were supposed to find direction as well. Okay, so we did not answer the question fully because the question wanted the electrostatic force. They did not want the magnitude only, so meaning they want magnitude and direction. Okay, so for direction you'd say theta is equals to arctan of what? Of the f of the y component divided by f of x component. Okay, so in this case, which one is our y component? So our y component is 1 3, and then x component is 1 2. So here we're going to say theta arctan of what? Of fy. Fy we say it is what? It's 1 3, ne? It's 1 3. How much is 1 3? 120 times 10 to the power minus 6. So 120 times 10 to the power minus 6 divided by 86.4. 86.4 times 10 to the power minus 6. Okay, so do say arctan of that 120 divided by 86.4. What do you get? You get theta is equals to 54.2 degrees. Okay, so now theta is 54.2 degrees. Remember that it's towards the left, so it's 54.2 degrees to the negative x-axis. Okay, so or you can say 180 minus 54.2, you say theta is equals to 125.8 degrees to the positive x-axis. Okay, that is your direction. So you will give this one or this one. Okay, so now let me leave the lesson here, guys. Okay, so there's another problem that I will do. Okay, it will be number 4, problem number 4, this problem. Okay, so but let me cut the video here.